The last section of 7.6 is how can we use all of our trig identities when we're solving equations and these identities appear. So we've done this a little bit already, okay? One of the main strategies that we've used already is trying to write an equation with only one trig function. And we've used sine squared plus cos squared equals 1. We did that in chapter 6. We had that on a couple of quizzes where if you have an equation that has a cos squared, you could change it to 1 minus sine squared. And if that changes everything in that equation to have only sine as the trig function, that's going to be helpful. But in addition to sine squared plus cos squared equals 1, we also have our double angle formulas, and when we write things with only one trig function, I've written in brackets here, we want things with only a theta, so if we do have double angle formulas, we'll often want to change them out. Other strategies, if you have a common factor, and sometimes you won't be able to change an equation to only one trig function, but you might be able to have a common factor. And finally, a strategy that we use in proofs also comes into equations. You're going to change to sine and cos and eliminate any fractions. Okay, so what does this look like for this example? We'll do this one first. It's a solve equation. It's not a proof equation, so you don't need to draw the line. At this time, we have cotangent equals 2 cos theta. I can go up for 2. I got excited. I'm sorry. I'll wait. Here we go. I'll move this out of the way. So in this equation, it starts with cotangent theta on the left and cos theta on the right. As far as thinking about this, the first thing we're going to try to do is change all things to a single trig function. Unfortunately, you can't change cotangent to just cos. You can't change cos to just cotangent. So that strategy is not going to work for us. So secondly, the thing that you might do is say, well, I'm going to change things to sine and cos. If I do that, well, cotangent is cos theta over sine theta is equal to 2 cos theta. And it says when you change to sine and cos, eliminate any fractions. Well, we have a fraction right now. We have cos theta divided by sine theta. If I want to get rid of that fraction, I would have to multiply both sides by sine theta. So if I multiplied this side by sine theta and this side by sine theta, well, these sine thetas would simplify and my equation would just become cos theta equals 2 cos theta sine theta. And at this point, this question is going to tempt you. It's going to tempt you to do something that I'll explain why you shouldn't do it, but you're going to be very tempted at this point to divide both sides by cos. And the reason you're going to be very tempted to do that, can you see if you divide both sides by cos, can you see your cos's just disappear? And you only have one trig function, which is like our main strategy for these. And so it seems like a really good strategy. And as a strategy, it will get you a bunch of right answers, but not all of the right answers. And the reason for that is if you divide both sides by cos, you might, without even realizing it, be dividing by 0, and dividing by 0 is bad. Taught you that through like all high school math. Dividing by 0, bad. Like I even got a picture over there of someone who divided by 0 inside their house and their house imploded, and yeah, it's just bad. So instead of dividing by cos, something that's similar to dividing is factoring. And so what we'll do is we'll move everything over to one side. And we'll factor out a cos instead. And what the factoring out does is the same thing as dividing. It separates things. And so now we have like two mini equations, right? Because when you have something equals 0 and you factor, what it means is either the first factor is equal to 0, in which case cos of theta would be 0, or the second factor is equal to 0. And if the second factor is equal to 0, then sine theta is equal to half. And in those mini equations, our trig functions are separate. And so solving for cos theta equals 0, when on our pi plate is theta equal to 0, or cos theta equals 0, our x coordinate, that happens at pi over 2 and 3 pi over 2. And when is sine theta equal to a half? At pi over 6 in quadrant 1. Oops. And 5 pi over 6 in quadrant 2. Did I give you a domain? Remember, whenever you finish solving a question, because we'll almost always solve it between 0 and 2 pi, we're going to check if there was a domain given in this question. And there was. It said solve between 0 and 2 pi. Perfect, that's what we did. So we're done. So in this case, this question used the strategy of we had to change things to sine and cos. We also had to use factoring because there was no way we could change our equation. When we had this equation right here, there's no way to change that all to the same trig function. We can't change sine to 1 minus cos. You can only change sine squared to 1 minus cos squared. Now, the next set of notes that we're going to add to this is with double angle identities. And the problem that occurs with double angle identities is when you have a question that says solve for x and it's cos 2x, you've seen questions like that before. They've been multi-revolution questions. But there's going to be some cases where you have to use the double angle identity instead of the multi-revolution. And so what this part in our notes does is explain the difference. When do we know it's a multi-revolution question and should solve it that way? And when do we know that we should use a double angle identity and change things? So for the multi-revolution questions that we've done so far, you'll know it's a multi-revolution question when the only trig function that you have is the double angle. So in the example that we have there, cos 2x minus root 3 over 2 equals 0. There's only one trig function in that entire equation, and it has a double angle. You'll know you have to use a double angle identity when you have a double angle and another trig function. So in this example, we have sine 2x equals sine x. Well, I have my double angle, but I have another trig function, sine x, on the right-hand side. That's going to be a question where we have to use our double angle identity and then see what strategies we can use from there. So with the one on the left, it only has the double angle, no other trig functions. So you would solve this like you would solve a multi-revolution question. How do we solve our multi-revolution questions? Well, first of all, I'll get the cos 2x by itself on one side. It's equal to root 3 over 2. Then you also take your domain and say, if 1x is between 0 and 2 pi, then 2x's would be between 0 and 4 pi. Root 3 over 2 is on your unit circle. For cos, that's part of the pi over 6 family. And so you would have 2x is equal to pi over 6 and 11 pi over 6. That's quadrant 1 and quadrant 4 where cos is positive. And then in the second time around, you'd have to add 2 pi to each of these. 2 pi is 12 pi over 6. So that will also give you 13 pi over 6 and 23 pi over 6. Then to solve for x, we could divide each of those by 2 or multiply by a half. And all 4 of those answers are between 0 and 2 pi, which was the domain that our original question asked for. So that question's review. You've had multi-revolution questions a fair bit. They're still difficult questions. They're harder ones to do. But if you have a double angle, up till now you only had multi-revolution as a method for solving. But now when you have a double angle, you have to make a decision. Will it be a multi-revolution, or will I have to use an identity? The second example is the one where you use an identity. So for sine 2x, because I have an extra sine x, I'm going to have to change my sine 2x to 2 sine x cos x and equal to sine x on this side. Again, you're going to be tempted to simplify by dividing here. Whenever you're tempted to simplify by dividing, instead move everything over, make one side equal to 0, and factor out the common factor instead. What this does is it separates things, so sine x could be 0, cos x could be a half. When is your y-coordinate 0? At 0, pi, and 2 pi. When is your x coordinate a half? Quadrant 1 and quadrant 4, pi over 3 family. So this question was very similar to the one that we did at the beginning of our notes, in that you had to factor it out, and you had 2 different trig functions. But this one we had to use our double angle identity. And finally now we can turn back to page 657 to example 4. We have 1/2 sine 2x minus cos squared x equals 0. So we have a double angle identity in this one, and it says solve. Do we use it as a multi-revolution, or do we use it as a double angle identity? Because we have the other function, the first thing we'll do is change the sine 2x to 2 sine x cos x. The 1/2 and the 2, those would simplify, and you'd have sine x cos x minus cos squared x equals 0. Again, we're always trying to get an equation to the same trig function. This one has sine and it has cos, but there's no way to change it just to have one of them. I mean, you could change the cos squared to 1 minus sine squared, but you would still have a cos in the first one. And so when that happens, your best option is to see if you could factor. In this case, we do have a cos in common, so I'm going to factor that out. And when I split it up, when I factor, I get One part I can solve for, cos x equals 0. The other part, sine x, would mean that sine x is equal to cos x. What do we do with sine x equals to cos x? Well, maybe you can just tell from your pie plate. When is the x coordinate and the y coordinate the same? 45 degrees. In any other quadrants, are they the same? Because in quadrant 1, they're the same. They're both root 2 over 2. In quadrant 3, they'll both be negative root 2 over 2. So you could solve this side. And the question's in radians, so I'll solve it in radians. Quadrant 1 and quadrant 3, just by knowing something about your unit circle. Your other option here is to divide both sides by cos. And then you would have sine over cos, which you could change to tan, and you'd get tan x equals 1, which is also pi over 4 and 5 pi over 4. When is cos x equal to 0? X coordinate equal to 0 at pi over 2 and 3 pi over 2. Solving for x or solving for theta is one of the key things that this year is supposed to teach you, grade 12 pre-calculus. It's so important that they put it in both chapter 6 and chapter 7, so you get to see it twice on 2 unit tests. It accounts for a major part of your exam at the end of the year. So now we are going to take some time to practice solving. Okay? Not only are you going to do the questions 12, 13, 14, and 15 out of your book, but on the identities sheet that you had all those proofs, on the back side is a full page of solving equations. So on the back side for the solving ones, if you have it, take it out so you can circle the following or highlight the following questions. 8, 9, I'll do WS for worksheet, 8, 9, 11, 12, 14, 15. Which is kind of confusing because on the back side I have some that are already circled, but those aren't the ones we're going to do. 21, 27, 29, and 31. So either do the ones out of the textbook first or the ones on the worksheet, and we are going to be solving these equations for at least the next 25 minutes.